Hello, everyone. Our project is based on the Mayo-Nero theorem. My name is Shwatan Patel.
My name is Vedant Amin.
And my name is Maharshi Patel.
Vedant will be covering the background, the introduction, the use and importance of the theorem, and the theorem itself. Maharshi will be focusing on how to prove languages are regular and not regular using the theorem. And I'll be focusing on the optimization and the language equivalence examples using the theorem. And so now I'll hand it off to Vedant.
Okay, so we basically will start with the background, basically what we have done throughout the semester, whatever we need to know to understand MNT. So starting with the formal language theory, um, a fundamental concept is a finite set of alphabets denoted by the symbol sigma. This set represents the collection of all possible characters that can appear in a language. And then we have clean star, which is denoted by sigma star, which represents the set of all possible strings that can be constructed using the characters from the alphabet sigma, including the empty string. A language in formal language theory is defined as any subset of strings L subset sigma star. In other words, a language is a collection of strings that can be constructed using characters from the alphabet sigma. For example, if we have the alphabet 0 and 1, then a language L over sigma could be the set of all binary strings that have an even number of zeros. And then we have a language is considered regular if and only if it can be recognized by a DFA or an NFA. In other words, if there exists a finite automation that can read the language and accept all valid strings while rejecting all invalid strings, then that language is considered to be regular. Another way to express regular languages is through regex, which is regular expressions. And then, however, not all languages are regular. So to prove a language is not regular, we learned pumping lemma for that. Um, so basically, this is the slide for introduction to Myhill-Narrow theorem, which is an important tool in the study of formal languages and automata. It provides a valuable result for understanding the properties of regular languages and finite automata. At a low level, MNT is a way to figure out if a group of words are part of a regular language. It does this by grouping these words into different equivalence classes based on the language. So if there are a finite number of these groups, then the language is regular. If there are infinite number of these groups, then the language is non-regular. So MNT basically helps to identify the distinguishing features of a language by examining the distinguishability of pairs of strings within the language. And distinguishable strings are those that have different outcomes when recognized by a finite automata. For example, in the language O to the n, 1 to the n, the strings 001 and 011 are distinguishable because they have different numbers of zeros and ones. On the other hand, indistinguishable strings cannot be distinguished by any FSN that recognizes the language. For example, the language A to the n, B to the n contains the strings A, B, and BA, which cannot be distinguished because they have the same number of A and Bs. So the set of all indistinguishable strings form what is called an equivalence class. MNT shows that there are a finite number of these equivalence classes if and only if the language is regular. This means that a DFA can be constructed to recognize the language. If there are an infinite number of equivalence classes, then the language is not regular and a DFA cannot be constructed to recognize it. Okay, so in this slide, we learn about the uses or importance of the MNT theorem. It can be used, as we saw, it can be used to check if a language is regular or not. It can also be used to reduce the number of states in a DFA while also maintaining the same language recognition capability. This is important because a smaller DFA requires less memory and can be executed more efficiently. So the number of states in a minimized DFA is equal to the number of distinguishable strings in the language. This means that if we can identify the distinguishable strings in the language, we can also construct a DFA with minimum possible number of states. Language equivalence is another application of MNT. It can be used to determine whether two languages are equivalent or not. If two languages have the same set of distinguishable strings, then they're equivalent. Finally, M&T can also be used to analyze algorithmic complexity of a language recognition algorithms. Specifically, the number of distinguishable strings in a language can be used to estimate the time and space complexity of algorithms that recognize the language. By analyzing the complexity of language recognition algorithms, we can improve their efficiency and performance. So this slide explains the whole theorem and its properties. So if you're given a language, L, and two strings X and Y, or the alphabet sigma star, we say that X and Y are indistinguishable over L if for every string Z in sigma star, either both X and Z, XZ and YZ are in L, or both are not in L. Formally, we denote this relationship as X L equivalent to Y, and we call it L equivalence. This is an equivalence relation, which means that it satisfies three important properties, which are reflexive, symmetric, and transitive. Reflexivity means for any string X, X is indistinguishable from itself. That is, X is L equivalent to X itself. Symmetric means if X is indistinguishable from Y over L, then Y is indistinguishable from X over L. So basically, if X is L equivalent to Y, and Y is L equivalent to X. And the last property is transitive. If X is L equivalent to Y and Y is L equivalent to W, then X is L equivalent to W. So these are the three properties of L equivalence relation that imply that sigma star is partitioned into disjoint sets called equivalence classes. In other words, strings that are L equivalent belong to the same equivalence class. So a language is regular if and only if equivalence relations of the language partitions sigma star into finitely many equivalence classes. If equivalence relations partitions sigma star into n equivalence classes, then a minimal DFA recognizing L has exactly n states. Now I'll pass it on to Maharshi to explain the remaining slide.
All right, so let's talk about the regularity about the Myhill-Nerode theorem. So let's begin with defining the language L, where W is a string where it consists of even zeros. So for example, L will contain the empty string 100, 0011, etc., but not 01, 000, since those strings show zeros are not even. First, we'll define the equivalence relation. We say that two strings X and Y in S are equivalent if and only if for any string Z, either all three of the strings X, Z, Y, Z, and Z are in language L, or none of them are in L. That is, if you're appending a string to X or Y, it either results in a string that is in L or it's not in L. Now we'll count the equivalence classes. And to show that L is a regular language, we will need to further show that the number of distinct equivalence classes of S is under the relation defined above in the finite, is finite. So let's use the same example from the previous slide, and we'll say consider any two distinct strings X and Y in S, and let Z be the string 0 repeated enough times so that appending it to X results in a string in L, but appending that same string Z to Y will result in a string that is not in L. So such a string Z exists since X and Y are distinct. Now, let's define W to be the string of 0 repeated enough times such that appending W to Y results in a string that is in L, but appending W to X results in a string that is not in L. Such a string W exists because YZ is not in L, but YW will be in L. Now, skipping through this, we'll say that, hey, similarly, since YW is in L and but XW is not in L, X and Y are not equivalent under the equivalence relations defined in the previous slides. Therefore, there are two distinct strings in S and are in different equivalence classes. So we've showed that the number of distinct equivalence classes of S under the relation defined in the previous slide is finite, which implies that L is regular by the NNT. So now let's prove the non-regular languages using the NNT. Let's define language L be 0 to the N and 1 to the N and the restriction being n is greater than 0 in the same language, alphabet, sorry. As you can see from the examples, we have to we know that some strings will not be in the set L, and to further elaborate, we have to consider getting two strings x and y with the same number of zeros and ones. So let m be the number of zeros, and we can write x and y in the form of 0 to the m, 1 to the m, and y as 0 to the k, 1 to the k, where k is also equal to m. Now, since we can see that x and y are distinguishable, there is a finite state machine that accepts x but rejects y, or the other way around. So without loss of generality, assuming that this position is the m plus n symbol from the left, we will have x equal 0 to the m, 1 to the n, y it will be 0 to the k, 1 to the k, and since the machine accepts x but rejects y, it must have entered in a different state after reading that m plus 1th symbol of x. However, since x and y have the same number of zeros and ones, the substring 0 to the m, 1 to the m plus 1 is a valid prefix for both x and y. So as you can see, this will be a contradiction since the machine cannot have two different states at the same time, which means x and y must be indistinguishable. In summary, any two strings in the language 0 to the 1, 0 to the n, 1 to the n will have the same number of zeros and ones that are indistinguishable, making this language have an infinite number of indistinguishable pairs of strings. And this does imply that this language is not regular as per the MNT. Now, using the MNT to prove other languages that are not regular, so we can see that we can see on the right hand side that there are examples where L is not regular. We cannot construct a DFA for these languages, and we need to have we need to look into the fact that there are infinitely many equivalency classes of L, and that's why L is not regular. Now I'll hand it off to Pratham.
So we use a theorem to prove that languages are regular and non-regular, and now we'll talk about some optimization strategies with the theorem, such as the minimization of a DFA. Based on the concept of indistinguishability of states, where two states in the DFA are indistinguishable if they cannot be distinguished by any string in the language recognized by the DFA. A DFA is minimal if and only if the number of indistinguishable states is equal to the number of states in the DFA. So how can we apply the theorem to minimize a DFA? Well, we can determine the equivalence classes of the states based on the strings that distinguish them. Then two states are in the same equivalence class if and only if they're indistinguishable by any string in the language. Then we can construct a new DFA where each equivalence class is represented by a single state. The transitions between the new states are determined by the transitions between the original states and the DFA. So the new DFA obtained in step 2 is the minimal DFA for the language recognized by the original DFA. This slide is an example of a minimization of DFA using the table filling method by the Myhill-Nero theorem. So here we have an example of a DFA. And so the first step is to draw a table for all pairs of states. So here we have this table. You may ask, why do we not have AA or BA, AC, all these this other half of the triangle? It's because it will be a redundant process, and we only need to consider only distinct pairs of strings. So the second step will be to mark all pairs where P is a final state and Q is not a final state. So for example, B and A are both a non-final state, so we don't have to mark them. But C and A, C is a final state and A is not a final state, so therefore it's marked. And so we continue this process for all the different combinations of the states that we have. And we can mark CA, for example, and then also we can look at F and E. F is a non-final state, E is a final state, so we mark those as well. And now the third step would be to mark. The third step is to if there are any unmarked pairs, for example, BA, DC, EC, then we have to look at the transition function. And then we'll mark PQ where X is an input symbol, and then we'll repeat this until no more markings can be made. So what do I mean by this? Well, if we look at this triangle here, we can see that F and FC is marked, right? So if we look at F and A, if F has the input 0, it goes to F. and then A has input 0, it goes to B. So F and B are not marked. But if we look at F taking the input 1 and A taking input 1, then we get FC. And we can see that FC is marked in this table. So since it's marked, we have to mark FA as well. And then the same follows for FB. So now we have this complete table for our unmarked and marked pairs. And then our last step will be to combine all the unmarked pairs and make them into a single state in the minimized DFA. So these 4 pairs are the unmarked pairs. And what do I mean by this? Well, these are the equivalence classes that we stated in the theorem. And for the n equivalence classes, we have n equivalence states for our minimal DFA. And so when we draw this out, we can see that these three states can be combined into one state. So technically, we only have 3 states in our minimal DFA. Next slide, please. So now we'll take a look at language equivalence. The Myhill-Nero theorem is a fundamental result in formal language theory. According to the theorem, 2 languages are equivalent if and only if they have the same set of equivalence classes. And so let's take a look at an example where language L1 is a language that contains at least 2 A's, and language 2 is a language that consists of at least 2 B's. So to apply the theorem, we can define the equivalence relation. 2 strings X and Y are said to be equivalent with respect to a language if and only if for all strings Z, the concatenation of Z, X, and Z is an L, and if and only if the concatenation of X and Y, if the concatenation of Y and Z is an L, or vice versa. So in other words, X and Y have to have the same behavior with respect to the language L. Now we need to find the Myhill-Nero equivalence classes for each language. An equivalence class is a set of all strings that are equivalent to X. And these are the set of all strings that are indistinguishable to X. If 2 languages have the same set of equivalence classes, then they will be considered equivalent. So for L1, the Myhill-Nero equivalence classes, if we recall, L1 is a language that consists of at least 2 A's. So here we'll have 3 equivalence classes. We'll have this equivalence class, it would be the empty string, B, 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 and basically the empty string and any number of B's, right? And then the second equivalence class would consist of 1 A, strings that contain only 1 A and an X number of B's. So obviously these 2 equivalence classes will not be accepted by the language. However, this third class will have at least 2 A's and they'll have an X number of B's. So this class right here will be accepted by the language. The same thing follows for our second language, which contains at least 2 B's. So our first equivalence class will have no B's and an X number of A's. The second one will have only 1 B and an X number of A's. And the third one will actually be accepted by the language. Will have at least 2 B's and an X number of A's. And then we can see that L1 and L2 have the same set of equivalence classes, which means that they're equivalent. This is because the equivalence classes depend only on the length of the strings, which are the same for both L1 and L2. So for example, if I take a string AABA, it has at least 2 A's, right? So it'll be contained in this equivalence class for the first language, and it'll also be contained in this equivalence class for the second language. So therefore, any string in the same equivalence class with respect to L1 will also be in the same equivalence class with L2 and vice versa. Therefore, we have shown that L1 and L2 are equivalent using the Myhill-Nero theorem. So to wrap up, why is this theorem important? Well, when we first took this course, we talked about regular and non-regular languages. We were given a criteria to prove that languages are non-regular, and we used the pumping lemma for that. However, we never really had a tool that can be used to show that a language is actually regular, right? We were just given regular languages, but we never actually were taught on how to prove them. So the Myhill-Nero theorem provides a necessary and sufficient condition for a language to be regular, which means that if a language fails this condition, it is not regular. And what is this condition? Well, we have to have a finite set of equivalence classes. And in practical terms, the Myhill-Nero theorem can be used to study or design and analyze finite set machines that recognize regular languages. For example, suppose that we have a language that we want to recognize. By applying this theorem, we can identify the number of equivalence classes of indistinguishable strings, which corresponds to the number of states in the minimal DFA that recognizes this language. This allows us to design an efficient finite state machine that recognizes a language with the smallest number of states possible. So we can see that the Myhill-Nero theorem has applications in compiler design, natural language processing, and other areas of computer science and engineering where regular languages are used to represent and process data. For example, it can also be used to optimize regular expressions, improve the efficiency of pattern matching algorithms, and identify common patterns in large data sets. That concludes our presentation. Thank you so much for listening.